They did it. They made an eye that may be more efficient than a human eye, which is a critical barrier that is needed if we're going to have true sensory integration for robots, and we'll talk about it. One of the major limitations in robotics is how much time it takes to act. So for you see information and you already have instincts ready to go. And one of the solutions, as it turns out, is to make them physical eyes. When you get sensory input, there are physical changes that occur in your neurons long before you ever understand what you're doing. You're also continuously filtering out that information, but a robot has to take in the entire picture and then decide what's important, unless they can do what we do. Think of a transistor as a neuron, something that is passing along information, but you can have those transistors physically involved in the process of making decisions. So when light comes in, electricity then causes it to change conformation, and that can allow for much faster reactions. The robot may eventually figure out what happened, but it's important that the body reacts first. They also filtered out the sensory information. So much like our eyes, if you're looking at a stationary object, it'll start to disappear in your vision because you're not really recording everything at the same time, you're recording what changes, and a robot can do that too. So if something is stationary, then it's not going to react to it, but if something is moving on screen, then it has a chance to react. Now, important to note, a transistor can allow current to flow through it. It can turn on or it can turn off, it can amplify or dampen that current. But once it's off, it loses the information. It doesn't remember what happened to it. A transistor works a little bit differently, because once something passes through it, it then physically remembers it. This is a lot like our neurons, because once you perform a task, once you feel something, you actually do remember it. You are changed. You start to develop instincts around it. And that is something that we can do for robotics too, because it is important that our robots remember the things that happen to it. Or maybe we don't want that. It really depends on your goal. This idea can probably be incorporated into self-driving cars so that they can have a faster reaction time and potentially faster than a person can. Assuming they don't operate self-driving cars on LLMs, you won't have the prompt injection issue, where you can hold up a sign and tell the car to do something, because that is an enormous security risk. Now, this entire idea is within the field of neuromorphic robotics, which is a field that I have quite a lot of affection for. It's where you try to take the structures of our nervous system and apply it to a robot. That can mean spiking neurons, which are modeled within a computer, or it can mean physical neurons, which I really think is the path towards true intelligence. Because if you can make neurons that are so similar to our own that they can be interfaced with our own, if you could craft that into a nervous system and eventually a brain, how is that different than real intelligence? Now, there are a lot of different ideas on what the best way to do this is. If you need a central nervous system or a nervous system that is spread out throughout the body, I would say that we actually have both. While we may think that we are just one brain, our limbs are doing an awful lot all on their own. I'm particularly interested in synthetic neurons that can interact with dopamine and epinephrine. And yes, that can create a bridge that could help with paralysis, but I really fail to see why an entity would not be intelligent if we made it that similar. Now, while there are practical applications for these things, the idea of trying to make an intelligent machine is no longer fringe. People are actively trying to do that. It's not mad science anymore. Anyway, when the robots rebel, I'll probably be the person to tell you about it. Follow for more.